Bernoulli principle explained using animation. There are several key assumptions made in regards to the properties of the fluid. Assume we have an ideal fluid. The fluid is considered incompressible. This means the density of the fluid is constant at any point along the pipe. The flow of an ideal fluid in a tube will be streamlined. Every particle in the fluid will flow along the exact path of any and all preceding particles. Each particle has the same velocity as that of its preceding particle. We shall use the principle of mass conservation to derive the equation of continuity. This principle states that the mass flow rate of an ideal fluid through a tube will remain constant at any point along the tube. Consider a section of the tube with a constant cross-section. Let us pick a point along this section and call it point 1. Say A1 is the tube cross-sectional area at point 1. Rho 1 is the density of the fluid on this cross-section. V1 is the speed of the fluid entering this cross-section. Say there is another point further along the tube where the tube cross-sectional area is different. Let us call this point 2. At point 2, we measure the tube cross-sectional area A2. We measure the density rho 2 and the speed of the fluid exiting the cross-section V2. Let us call delta m over delta t the mass flow rate through a given cross-section at any point along the tube. This mass flow rate is constant. The mass flow rate is the product of density by the tube cross-sectional area by speed of the fluid at that point. For any given fluid, the mass flow rate through any given cross-sections along the tube are equal. For point 1 and point 2, we then have this equation. When the fluid is an ideal fluid, the density of the fluid at all points in the tube are equal. Therefore, the product of the fluid speed by the cross-section area at both points are equal. This means that the product of the fluid speed by the cross-section area at any point along the tube is constant. This is called the equation of continuity. Say we have point 1 and point 2 at different heights. We then use the equation of continuity with the principle of energy conservation to derive Bernoulli's equation. Let us say P1 and P2 are the pressures of the fluid across the tube cross-sectional areas at these points. This equation shows how the pressure and velocity and height difference of a flowing ideal fluid between 2 points in a tube relate to each other. The net work done between the 2 points is the difference between the pressure P multiplied by the volume V at each point. The volume V of fluid flowing in the over tube is the same along any given point of the tube. This means that V1 equals V2, which equals V. The work done then becomes P1 multiplied by the volume V minus P2 multiplied by the volume. The work done also equals the change in potential energy PE plus the change in kinetic energy between these 2 points. The work done between these 2 points can then be made into this equation. The work done also equals the change in potential energy PE plus the change in kinetic energy KE between these 2 points. Arranging the terms, we get this. Dividing by the mass m, we get this. The density of the fluid ρ is the volume V divided by mass m. The equation then simplifies to this. We can then simplify the terms even further to finally get Bernoulli's equation. From the equation, we can derive Bernoulli's principle. Assume that the height h between the 2 points remains fixed. The equation shows an increase in the speed of a fluid V will result in a decrease in pressure P. Bernoulli's principle is a bold statement, as it is counterintuitive that an increase in fluid speed would result in a decrease in pressure. We can now explain how Bernoulli's principle can be applied to our example. As the cross-sectional area A1 is greater than A2, then the fluid speed V1 is less than V2. Using Bernoulli's principle, we can deduce that the pressure P1 will be greater than P2.